Hi everyone, this is Akbar Arif and welcome back to our Building Large Language Model from the Ground Up series. In the previous lecture, we have discussed about pre-training and the fine-tuning. That is the two stages that are involved in building large language models. So today we are going to talk about something extremely important. So think of something like if LLMs are the brains, then transformers are the nervous system that makes everything works. So today's topic is simple. What are transformers? Don't worry, I'm not going into heavy mathematics and the coding part today. I just want you to understand the intuition clearly. Once your intuition is strong about the transformer architecture, the maths and the coding part becomes like super easy for you guys. So let me take you back to 2017. In 2017, a paper was published called "Attention is All You Need." Well, this is the paper. "Attention is All You Need." It was published in 2017, and the authors were from Google Brains. These are the authors, and let me show you the proper transformer architecture. Well, this you can see is the proper transformer architecture. Here it involves the encoder part, and this is the decoder part. So we will be learning about all the terms inside it, like for example there is multi-head attention, add and norms, feed forward. We will be knowing all of these things in the further lectures, so you don't have to worry about this. So well, honestly, this paper was revolutionary. This changed the AI world completely. Before this, we were using RNNs, LSTMs. They were good, but they had some problems. They struggle with long sentences. They process text sequentially, one word at a time, and the training was like absolutely slow. So then this transformer came into the picture, and suddenly everything becomes faster, more scalable, and much better at understanding context. So actually what is interesting about the transformer is that it was not originally built for ChatGPT. It was built for machine translation tasks such as English to German conversion, English to French conversion. So nobody at that time imagined they would power conversational AI. Now let me simplify what actually transformer is. At a very basic level, a transformer is just a deep neural network, but the key difference is this: that instead of reading a sentence word by word like older models used to do, transformer looks at the entire sentence at once. And that's something that makes transformer so powerful, because language understanding depends on the context, and context doesn't just come from the previous words. It can come from anywhere in the sentence. So let me show you one example that how the workflow in the transform architecture flows with respect to the language translation. So over here I have prepared a GIF for you guys. So here you can see basically it is converting English to German. So here you can see that these words are converting into tokens, then token IDs, then vector embeddings, then position embeddings. Then these position embeddings are going to the decoder part, and then the conversion from English to German is happening. So let me just walk you through a simple example. I've prepared one presentation to show you. Like if suppose we input a sentence, for example this is an example dot, not so obviously the model doesn't understand English like we do. So the first thing it does, it break the sentence into smaller units called tokens. So we will be dividing into chunks, these words into chunks. Like for example you can see our input text is further divided into chunks. Well, that is known as the tokenized text, and the conversion of this tokenized text is known as tokenization. And afterwards we are converting this tokenized text to the token IDs. So why we are converting this to the token ID. So like each token is assigned a numerical ID because neural network doesn't understand the words, they understand the numbers. So that's why we are converting these tokenized text to token IDs. Now the things from here will get more interesting. After the tokenization, the model converts these tokens into the vectors. These vectors are called the embeddings. We are converting it to the first the token embeddings, then the position embeddings. Well, the positional embeddings I will discuss in the another lecture. You just have to know that we are converting these token IDs into the token embeddings. So, for example, now imagine a huge mathematical space where similar words are close together. Uh, like I will tell you why this token embedding is created out of the token IDs. Like for example, the word king and queen would be close. The apple and banana would be close, but the banana and the car would be far apart. And this is how the model captures the semantic meaning. So embeddings are basically mathematical representation of the meaning. So for example, like this word has a vectorized embedding over here, and this will be also factorized. So our model will be trained in such a way that it will be able to find some semantic relationship between these vectors. So basically we have to convert all the inputs text to the the embeddings, and through that we are going to train our model, and after that they will be the model will be finding the semantic meanings between each tokens. So now comes the most important part of the transformer. Well, that is attention mechanism. So have you guys have just thought why this paper is called the attention is all you need? Because the attention is the heart of this whole architecture. Let me explain it simply to you guys. Uh, suppose if I say Harry boarded the train and he was late. Now when we read this, we instantly know that he refers to Harry, right? But how does the model know that he refers to Harry? So throughout that, something called self attention comes into the picture. So self attention allows the model to look all the words in the sentence and decide which ones are important for predicting the next word, right? So attention is something it will find the meanings that this word is related to this word. Okay, so it is basically providing some intelligence to the words that these two words are interrelated to each other. So it actually assigns the importance score, and it basically asks that which word should I focus on. Maybe the first word is important, maybe a word 5 position back is important to this particular word. So attention allows the model to capture long range dependencies through this uniqueness it shows, and that is why the transformers are so much powerful. So now let's just talk about the structure. The original transformer architecture has two main components. One is encoder and second one is the decoder. As you can see over here, this is the encoder part, this is the decoder part. So the encoder takes the input sentences, processes it, and then convert it into the embeddings. The decoder takes those embeddings and generate output one word at a time. So in translation, the encoder reads the English, as you can see over here. The encoder reads the English, and decoder generates the German over here. It is gone into the decoder part. Well, this part I will explain, and after that the prediction with the language translation is been done. So let's just talk about the BERT and the GPT. What are the differences between these two architectures? So BERT stand for bidirectional encoder representation for transformers. It uses only the encoder part of the transformer. So there's a clear difference between the BERT and the GPT, that BERT uses the encoder part of the transformer, and the GPT uses the decoder part of the transformer. So during the training, the BERT actually hides some words in a sentence and try to predict them. For example, you can see over here, if we are inputting this text, this is an dash of how concise I dash be. So so actually it fills in the missing words to generate the original sentences. So the board acts in such a way that it will fill in the blanks with the text we are giving it. So this is, so over here you can see that it has generated the word example and can. So it receives the word where the words are randomly masked during the training. So this is how the BERT model is trained. Now we will be looking out for the GPT model. So the GPT stands for generative pre-trained transformer. GPT only uses the decoder part of the transformer architecture. It doesn't predict the missing word in the middle as the BERT does. It predicts, so actually it predicts the next word. So if I write this is an example of how concise I can. So it will further predict the next word. So that is B. So so it was designed to for the generative task and producing coherent text sequences. So this is how the GPT is able to generate the next word. So basically it is a generative model, so it generates the next word as it is written in its name as well, generative pre-trained transformer. Now here comes something really important about transformers versus LLMs. So do you think like our transformer and LLMs are same? Well, according to me and according to the books and the whole research paper, they are not the same. Not all the transformers are LLMs. Transformers are also used in the computer vision tasks such as image classification, medical imaging, object detection, and many more. And not all LLMs are transformer either. Before transformer, we had a language model that was based on RNNs or LSTMs. So remember this clearly. Transformer is an architecture. LLM is a large-scale language model. They overlap, but they are not identical. So let's just read this out. Today's LLM are based on transformer architecture. Hence, transformers and LLMs are terms that are often used synonymously in the literature. However, note that not all the transformers are LLMs, since transformers can be also used for computer vision tasks. Also, not all the LLMs are transformers, as there are large language models based on recurrent convolution architecture (RNNs) and LSTMs. The main motivation behind these alternative approach is to improve the computational efficiency of LLMs. However, whether these alternative LLMs architecture can compete with compatibility of transformer based LLMs, and whether they are going to be adopted in practice remains to be seen. So as you can see, like transformers can also be used, transformer architecture can also be used for the computer vision tasks, as well as I will show you some research paper in which the transformer architecture has been used. So I have taken out the Swin transformer. So basically this research paper is basically for the vision based task, and this is the another paper that is VIT, vision transformers paper. It was the first research paper that uses the transformers for the vision specific task. And here we have pyramid vision transformers, and we have DIET, training data efficient image transformer, and we have CBT as well. So I will be teaching you all of these architectures as well in this course. I know that these architectures are not related to our specific use case. We are building large language model, but still, I think so. By reading this research paper, you will get the proper understanding about further things as well. Like if you want to modify your transformer with some another transformers, like the swing transformers, so you can make changes in the architecture as well. So let's just quickly recap that what we have done so far in this lecture. So we have learned that the transformers was introduced in 2017. This was the paper, and then we have seen that how the tokenization is happening and why we need to convert it. Why we need to convert these texts into the token embeddings, and after that we have seen the self-retention mechanism, that why it is so important in the transform architecture. And then we have seen the encoder decoder part, and like GPT uses the decoder part of the transformer block, and BERT uses the encoder part of the transformer block. And then we have seen that transformers and LLMs are not equal over here. So this is just this is just the foundation of this whole large language model building thing. So in the next lecture, we will go deeper into how attention actually works, what is query key and values, and how the maths behind it works. Of course, we will not be going into the coding part yet, because we are first covering the mathematics part of it. And I just want you guys to build a proper intuition about how the things are working inside the transformer block and how the GPT is built. So, and other thing I just want to recommend you is that you guys should read this paper as well. Even if you don't understand that what is going inside it, you should make a habit to at least read a research paper in a week, because it will boost your actually it will boost your data science career for sure. So this is Akbar Arif, and we are building LLMs from the ground up, step by step. And I will see you in the next lecture. Well, thank you.